I built this mirror array using tiny actuators, dozens of them, each with sub-millimeter accuracy, to reflect light on a wall precisely. In theory, it should work perfect, right? In practice, the reflections were all over the place. Today I'm going to show you why motor accuracy is not enough in itself, where those errors are actually coming from, and how I improve the system using camera-based software calibration. I will also share my struggles and learnings using AI to code this system from scratch.
Welcome to TimeSync Studio, down the rabbit hole. So what are we trying to fix? The mirrors are arranged to a grid. If we zero all the motors and move them to center, the reflection should be a grid too. But that's what we get. What is causing this?
There are multiple reasons why it's happening, and all of these adding up together on different level for the inaccuracy. One is being that the motor itself has a backlash. So even if it's in position, you can see it's moving a little bit back and forth. By the way, for that, I got really good tips in the comments, so I will get back to potential solution for this. The other issue is the motor has a little spring on it, so you can see it has some movement. Also, my design itself using ball joints. So these ball joints have a little wiggle, and maybe I will make a whole video about 3D printing ball joints and all 3D printing challenges, but this is obviously causing some wiggle and some inaccuracy. The print itself, even if the printer is very well calibrated, there are some sub-millimeter differences as well. On top of that, I printed this grid which holds the mirror tiles from PETG. I can talk more about that choice, but PETG, the material, has some flex, more flex than let's say PLA, so it's causing the distortion. And also, if you look at the assembly, if I tighten one screw more or less, it has some differences as well. So what could we do with this? I received really good tips on my previous video in comments. Thank you for that. One of them was to put some tension on this tile to reduce the backlash of the motor. So tension could mean that we put a spring or a rubber band to pull this tile back, so it would definitely reduce the backlash on the motor. On top of that, it would also help this wiggle against this wiggle in the ball joints. That's definitely something I should look into in future iterations. I think that would be a really big win and it would improve a lot. However, it wouldn't address all the challenges what we have, like the differences in the 3D prints, the assembly, and also the matrix itself, how is it flexing. And we also have another challenge which is independent, but could we do two birds with one stone?
Let me very briefly recap the calculations from my previous video. In order to achieve a displacement on a wall, we can calculate the angle, the tilt angle of the mirror based on these formulas. So if we have this angle, we could convert the steps into angles and calculate how many steps we have to make with the motor to achieve this displacement. So going with this logic, initially I thought, let's just do a calculation. For this, I even created a little visualization calculation. I use Babylon.js. It's a JavaScript library which I didn't know before. It's quite good. You can in browser do these calculations. But anyway, based on the incoming light, we can calculate the mirror angle in both axes in order to achieve the reflection on the wall. However, there are some challenges with this. First of all, there are a lot of parameters. We have to know the wall distance in order to calculate the right angle. And we also have to know what's the wall angle compared to our mirror array. And we have to know also the sun direction, both the horizontal and vertically, where is it on the horizon, in order to calculate the angle as well. But once we have this, yes, we could in theory calculate, or in practice as well, we can calculate the actual angles. So here you can see both angles of this selected mirror. So what is the angle of this mirror required to have that reflection on the wall. But this doesn't actually calculate in misalignment or the issues I mentioned before with the printing and so on. So all these issues are actually not tackled with this. Is there a better way to solve this? So what if we place a camera on the top of this mirror array looking at the reflection, and while we are moving the motor and doing the steps with the motor, we track the light reflection displacement on the wall. if we could do this, we could convert the steps directly into displacement on the wall. And not only that, we don't need the calculations for the angles, but we wouldn't need to enter all these parameters or calculate where is the sun and how far is the wall and what is the angle of the wall compared to the mirror array. Even better, this would mean that this would actually count in any mechanical inaccuracies what we discussed before. This sounds good, but how could we do this? My initial thought was, let's train an AI model for this. We are called TimeSync Studio, but that would have been a total overkill. It's a much simpler challenge. There is OpenCV, which is an open source image processing library, and I hope that it will be more than enough for this challenge. I'm not familiar with it, so I created this little playground where I can test the different processing methods and figure out what works for my use case. So the OpenCV Playground I quickly wild coded and created is on the left side here. You see the input image, and the right side is the processed image. I also projecting one square right now. The first thing that we do is like downscale the image, because anything higher is very slow, but actually it's also making less reliable the detection. Brightness contrast is just to tune a little bit the image, but the other processing is must-have is grayscale. We are looking only for contrast and brightness differences, so that really simplifies the whole processing and makes it actually work much better. There is this normalization which I found useful to add. What it does, it's a little bit making the brightness, the contrast much more prominent, so it's easier for any detection algorithm to work on this later. So I went through a lot of different approaches here and play with them. If you are familiar with OpenCV, please comment. I'm pretty sure you have some good tips which I could use here. Just very briefly, I'll show a few which didn't work. Adaptive threshold, which actually really nicely you can see found the edges of this, but it brings so much noise, it would have been really hard to figure out where is the blob. At the end of the day, blob detection was the best to do this. So what you see here, if I add this blob detection into this processing pipeline, and I also display the detected blob with a circle, it's actually found this square very nicely. What the blob detection returns is the coordinate of this spot or the blob it found, and also the size of it. There are a lot of settings, like minimum area we are looking for, so if I increase it, it won't find, and so on. But this worked surprisingly reliably, and it's also I tested with sunlight, which like different size of this spot and different brightness contrast. It works really nice. Very little tuning needed for the image pre-processing to find the blob. So we can find one blob, but when they are overlapping, you can see the overlapping blobs we cannot detect this method. This led me to the realization that I have to do this one by one. There is no way, at least I couldn't think a simple way to figure out which motor belongs to which spot. Obviously I could make track movements and check which blob moves, and there are ways to do that, but that was like far more too big, too deep rabbit hole. So I will show you how I built the calibration using the single blob detection. So this is our uncalibrated home position. Then the calibration starts motor by motor, one by one. It's a bit hard to follow, so I will pause and explain step by step. A couple of things on this UI. It's very convoluted because I was just throwing in new features. It definitely needs a cleanup. But this green box, what I can adjust is the region of interest for OpenCV. So what it does, it actually limits the image what goes into OpenCV. You can even preview it. If I select row view, that's what OpenCV actually processes. You can already see the blobs detected on this image, but as we mentioned earlier, there are overlaps, so it cannot detect all the blobs what we have. So in order to do this, first we have to actually make sure that we know where the motors are. And if you recall from the previous video, we do a homing first. So this is going to be the first step I'm going to execute. I have this option for doing step by step. It's primarily for debugging, but it's really useful now to explain step by step what's happening. So when I start the process, all motors went to the extreme, and then we move back to the middle position. And the next step is to move the motors aside, so they are not interfering, they are not overlapping the light spots.
I'm switching to process so you can follow what's going on, or you can see the blobs. So now everything is stage position, and the next step is measuring the first tile. So a lot of things happening here. It will be a bit faster explaining, but the first thing what you see is this blue circle. So this bluish circle is the expected position where we expect the spot to be in. We don't know exactly where the center is, but we start with a very big one. We don't want this detection to pick up the wrong one. You can see the side one is marked as well. So this is the way how we look for the closest in this circle. The other thing you see here, visual indication of the physical center of this blob, where this spot is physically. At the beginning, this is actually overlapping for the calibrated home for this blob, which is the steel square. And as we go, we will improve on this. The next thing we have to decide, because we don't know how far is the wall, we have to measure that how big movement is one step. So what we do first is do an interim step, a very small one, because we don't know the distance of the wall. We measure this displacement of this blob, then we move this to the extreme. Because we measure the small step displacement, we can already predict where we expect this. You can see the circle for the side to the extreme side movement is not too far off from where the blob ended, but we record this, and then we also do the same for the y-axis. So we move it here. You can see we expected it here. It's not exactly there, but we record this, and when we move this tile aside to the staging position, because with this tile we are done now. We move in the next one, and now at this point we start to build up, because we have better understanding of the geometry of the projection. We can start to build up this ideal or blueprint grid. And as we go step by step, our predictions are getting better. You can see it's almost exactly where we expected. And the same for this. And every step is getting better and better with this prediction, assuming the tile is accurately built on. And this continues and it improves, and ultimately it's built up a grid, an ideal grid, which is adjusted and corrected for each tile individually. These yellow dots are actually representing very well how chaotic this build is. So we're getting to the last ones. So what will happen now, it will align to this ideal grid. And voila, suddenly we have a calibrated grid. We still have a lot of displacements. We talked about lack of tension and the misalignment with the printing, but this is close enough. So now if I go to the patterns and I play back any pattern, and I can also with the pattern editor, whatever I designed, I can move to the position. So is it perfect? Definitely not. You can see the misalignments, most of them coming from the fact that I mentioned earlier, all the lack of tensioning and the assembly, but we couldn't actually get even so far without this calibration. And I would say the beauty is in the inaccuracy. We are analog end of the day. And most importantly, I can focus to one point all the mirrors. Stay tuned for the next video. And I also promised to go into learnings of vibe coding. This video is getting really long. I'm just going to show this new feature development. If you are interested in more details of how we get so far with this system with vibe coding only, I'm more than happy to do a future video. Just leave in the comments. But let's have a look for this vibe coded feature first. For recording the video, I needed a feature to actually be able to continue and finish to the end. So the recording has the end to end. So what I thought to add now is a feature where when I'm in step by step, I can finish it with a click, and it just runs without interruptions. So let's see how I can do it with Claude Code. Live vibe coding. I usually use this plugin because it goes through certain questions, and it has quite good prompts in Claude Code to drive this new feature development. And I also, when I'm especially lazy, I just use Super Whisper, which I whisper, which is just easy. I don't have to type. I have the calibration, and there is an option to do it step by step. It works great, but I would like an additional option, which when I'm in the step-by-step process, when I click this or select this, then it finishes the process without any more interaction needed. So it runs towards the end just as normal. So what Claude Code does is now is bringing in the necessary context. If you go to the repo, you will see the Claude MD, and the Claude MD has some points where the Claude can start. I even generated this mapping with Claude. So what it does is actually going through the source files and understanding the code, and then it will come up with a few questions around the feature before it starts to implement. You can see the plan. So it finished exploring the code base and it came up with a few questions regarding to clarify the requirements. So where should the run to end button appear in the UI? Let's say here. And this is a fairly simple feature, so actually there are more. Yeah, I think it should work the same way as it works. So we have like a retry feature even when it's in continuous mode. Permission to continue without started to implement it. So it asks for permission. I just say yes, allow all edits. I trust I can always revert. It's all under version control. So now it reported finished. So let me show what it did quickly. It implemented the feature, but also was designing with sub-agents, the architecture and so on. And I have a lot of tests. I was pestering constantly Claude to implement unit tests. So it also ran those tests, but we still have to try it. So let's have a look what it did. I look at the calibration. Hopefully we have the option when I start. You can see the run to end button is here. If I go step by step, then it works, and I click run to end, fingers crossed, it's actually running by itself. Obviously a bit more manual testing is needed, but it created the feature in how many minutes? 6 minutes, maybe? 6 minutes, 7 minutes, with a single input, a single voice input prompt from myself and a couple of clarifying questions. So obviously it doesn't work always so nice, but I think it shows like how quickly you can code if you are using the proper tooling and the proper unit tests you have around. The repo is linked in the description of the video, and I will commit this so you will see all the changes it made in the code base.